All right, well, I think we'll get started this morning. Good morning, everyone. My name is Mike Larson. I'm a field engineer with Keysight, and I've been with the company for 39 years. Thank you for taking time out of your busy schedules to join us for this virtual seminar on the topic of electromagnetic properties, characterization of materials. We'll be covering several different measurement techniques today with details on the solutions that are available for the various use models of this application. If you have a question during the presentation, please type your question into the chat window to all organizers. Our team of chat moderators will log the questions and they'll be addressed after the presentation has concluded or possibly during the presentation, depending on how we're doing on time. All participants are currently on mute. However, if you'd like to ask a question using the audio feature, you may hit the mic button on your panel to speak live with our presenter. Otherwise, please keep your microphone muted to eliminate any possible disruptions, which is one of the unfortunate byproducts of working from home, like most of us have been over the past year. We're always working to optimize your experience while attending these events, and today we're using a new platform, and your feedback is critically important to help us continue to evaluate and improve these events. At the end of the session, we'll have a very short evaluation, only 5 questions. If you'll be kind enough to complete and submit the evaluation, it will be most helpful and very much appreciated. Our presenter today is Sai Famakasan. Sai is an application engineer at our RF microwave division in Santa Rosa, California. He's acquired over 40 years of RF microwave and millimeter wave measurement experience while working for Hewlett-Packard, Agilent, and Keysight Technologies. For the past 25 years, he's worked in customer support, sales, technical support, and product marketing. He's developed and presented training materials for internal and external customers on a wide variety of network analyzer measurement topics, including materials characterization and antenna tests. Sai is also currently working with our Keysight Solutions partners to bring the latest solutions to the materials measurement and antenna test industries. So without any further delays, let's get started. Sai, please take it away.
Okay, thank you. Thank you for your time and thank you for calling in for this presentation. My goal is to share with you what solution available today from Keysight. Also share with you some of the different measurement methods, so that way you can choose which method is best for your particular materials. So this is the outline for my, let's say, 45 minutes or so talk. So first, I'll cover some market trends and definitions, and then why material measurements matter to you. Then look into more details, perhaps high level of measurement solution available. And then at the end, I will make one recommendation so that perhaps it may fit what you want to consider as parameter when decide what method to use, and then open up to questions and answers. As Mike said, feel free to ask as go along, and that way may be more effective. With that, so in terms of market trend, I think everybody knows by now 6G is many people research in this area in the FR2 as well as in millimeter wave, 28 gigahertz, 39 gigahertz. In addition to that, the automotive and energy area also do a lot of materials, especially nowadays at the millimeter wave frequency is critical because how signal propagate affect greatly by the dielectric properties. In addition to that, aerospace defense, traditionally many of these industry or area of this material research, because the solution normally are available at lower frequency, so they measure and characterize low frequency and then extrapolate up into high frequency. With that scenario, a lot of times could cause, if your measurement is not accurate at low frequency, when you extrapolate to high frequency, can cause a lot of problems too. So these are a sample of what material we test. Basically, we have solution all the way from the PC board substrates to biofuels that we can characterize all your materials. Some area in the Southeast Asia country, a lot of times, agriculture, they even test some fruit, and then, stale material, liquid, thin sheet, phantom material, all those material we have the solution that we can test, depends on your frequency of interest and so on and so forth. So I think you probably know by now. I just want to make sure and remind some of the definition. So when materials interact with the electric or magnetic fields, two things happen. The energy is transferred bidirectional from the electric or magnetic fields. So we call that storage, or that is representing the real part of your permittivity. Another part of that is the loss, meaning that the energy is transferred by one direction, and these could be the loss to the heat or do some other effect on materials. So this is true regardless of your material is magnetic material, permeability, or permittivity. Another term I just want to remind you is that the loss tangent. The loss tangent is one term that describes the relationship between the real part and imaginary part. And some people call this a quality factor, or most people also call tan delta, loss tangent. DF is all the same terms, meaning the same thing. So why material management matters? So as I mentioned a little bit ago, that signal propagates through transmission line to some other material that affect by actual material itself. Ideally, that when signal propagate to whatever material or media or transmission line that you propagate or transmit your signal, you want to be like error, means nothing there. Unfortunately, that's not how real world material affects the signal propagate. The decay or the permittivity value or dielectric constant affect the signal delay or signal latency. As you can see on the right side of the screen, different permittivity or decay value, the signal propagate has different delay numbers. For example, alumina have the permittivity value roughly about 10, and the signal propagation delay is roughly about, let's say, 10.5 nanoseconds per meter. The same is true with the DF or the loss tangent value. So these parameters affect how signal loss. So ideally, you want these to be as low as possible. That way, you don't waste energy or power during your transmitting. So most of the requests now, because of 5G and also automotive radar high frequency, so people characterize around 30 and 80 gigahertz. Another example of how these affect the example of how DF affect your actual signal conditions. On the left side is simulation equivalent of 3 centimeter transmission airline have different DF value or loss tangent or tan delta. So the top one is 0.05. You can see the eye diagram that open up nicely. That means less effect on your signal. As the DF increases, you can see that the eye is closed, and in this case here, 0.15, you can see that disturbs your signal quite significantly, so it affects your signals. Okay, so that's why DF decay is critical when you do the material research or when you design circuit or some other material. That's how it affects your signal. So now comes to what do I do, or how can I make these material measurements? So basically, when it comes to material measurement, you need some sort of software. Perhaps these can be, mini university. Perhaps you can do it themselves, because all the formula, some of them are public domain. What Keysight provides is a comprehensive software control mini instrument. So the second part is the actual instrument, RF instrument, LCR meters, or impedance analyzer. So it depends on the measurement method as well as your frequency of interest, and many times also depends on the budget. Okay. And then third part of that will be fixture. So fixture, we have a variety of fixture, depends on, again, what measurement model that you're going to choose. On the right side, we have different measurement model, and also depends on your sample restriction. So Keysight, like I mentioned, the N1500A material management suite software control all Keysight instruments, including the very high-end mmWave system, in this case, broadband up to 125 gigahertz, even in terahertz. Field Fox, handheld product, LCR meter, impedance analyzer. In terms of network analyzer, we have, the benchtop, the PXI version, more multi-port, USB, streamline, more low cost, more portable, also ENA, the part of network analyzer. And in terms of measurement model or methods, so we have a variety of different methods, which I will go into specific of each of these methods in next few slides. Okay, so this kind of map showing that all the measurement available from Keysight technology, and on the left side, the vertical is your material types. So the liquid, gel, semi-solid, powder, solid substrate, toroid core. So and the frequency is on the bottom. So in other words, is let's say you want to measure only up to 1 gigahertz. In this case, maybe some of these fixture may be good for you, because we can measure both magnetic and non-magnetic materials. And the next one is the probe. The dielectric probe is most convenient solution available. The reason I say that, because you don't have to prepare your sample that much. You can measure liquid, gel, powder, as well.
How are you? Thank you.
So I hear some echoes.
Can you mute everyone?
Everyone looks like they are muted. If you're not, your phone.
If all the participants could please check to make sure that you are currently muted. We are hearing some background noise.
Thank you.
Can you hear me?
Yes.
Okay. So the dielectric probe is the most convenient and most some early research people usually use this dielectric probe, because when you don't have to do too much to prepare the sample. In addition, you can measure your solid material as long as your surface is really flat, like your computer screen flatness. And this is operate up to 50 gigahertz. The other method is called transmission line method. This transmission line method mostly aim at higher frequency, simply because the fabricate sample into inside fixture may be difficult, and then we can use coaxial or waveguide. Another one is called resonant cavity method. This is for low loss. So this, if anything else, for selection of your material, refer to this table. I think will be helpful when you make your purchase decisions. So let me go into individual methods. Parallel plate, basically we are using two electrodes. For the top and the bottom, the yellowish color is your sample. And when we sandwich the sample into these two electrodes, and we measure the capacitance and admittance of that, and then from that we can calculate the permittivity using this formula. Of course, this method you want to minimize the air gap. The air gap introduce measurement error. So that's when you prepare your sample, you need to be consider of the flatness and make sure the material is flat all the way across. It comes with 4 different electrodes that can measure your material, depends on the sample that you want to measure and the thickness. And the solution in this case is really low frequency, up to 30 megahertz only, using the impedance analyzer or LCI meters. So if, as I previously mentioned, the air gap. So because air gap is large and then affect your measurement. So I won't go into the formula here. Let me actually show you the actual table. So this is your permittivity or your decay value on the top, and this is the ratio of your sample and the air gap. So if your permittivity is 10, your air gap is 0.01, then your measurement error is 1%. Obviously, the decay higher, your measurement error is large number, as well as your air gap is large, and then affect your measurement. Most of the people nowadays do material measurement. Usually, the decay is between 2 and 4. So especially at higher frequency, they want to get really low decay and DF value. Because we are using the impedance analyzer, so we have to make sure that the measurement range is within the measurement capability. On this graph shows that the black solid line is the measurement zone. And so this example shows that the blue dotted trace is the decay is 10 and the thickness is 1 millimeter. So when thickness is increased, and this could affect your measurement zone. So in that case, that perhaps you have to trim or change your thickness to be thinner, so the way you move your measurement zone down to the center of the measurement zone area, so that you can make measurement more accurate. Okay. So this solution up to 1 gigahertz. So the difference from this solution from previous is the frequency is higher using different fixture. In this particular case, the fixture has the spring load, so that you don't have an air gap problem. However, if your sample is soft, then it may affect your thickness. So one of the parameters of material measurement is we need to know precisely the thickness of your material, because thickness is used to define or to calculate your permittivity. And in this solution, we incorporate different type of calibration so that it has better accuracy compared to the previous solution. Again, come with a couple of different sample electrodes. The same scenario here. Yeah, it has a measurement zone. I wouldn't go into details. So what is good, what is bad about these low frequency parallel plates? So relatively simple computation. As you can see, the formula works well with thin sheet, the PC board film. Inexpensive, of course, depends on your point of view, and it's best for low frequency. The limitation, as I mentioned, stop at 1 gigahertz, and sample to be flat and smooth sheet. In terms of magnetic measurement at low frequency, we do have, again, parallel plate method. but we measure actual inductance. So in this case, we have different fixtures, and using the same base instrument that we can use this formula to calculate your permeability or your mu. Okay. This is a more detail of the actual fixture inside, the sample size and thickness. So now switching to the measurement method number 2, coaxial probe. So coaxial probe basically using the network analyzer. This is using the reflection coefficient measurement. The software can run inside the network analyzer or external PC. How it works or what instrument is compatible with, as I mentioned, Firefox, USB VNA, as well as the PXI box. So when you have PXI instrument or you have 4 port like this, the software allows you to have multiple probes. So that way, sometimes some of the measurement that you want to measure different areas of your sample, that way you can measure all different locations simultaneously. So how it works, if you're not familiar with the S parameter, this is measure reflection coefficient. Basically, the signal will go through this probe. This is open end probe. We simulate the material and we measure the reflections. So the sample assumption has to be effectively in finite thickness, or normally what we say is 20 divided by the square root of the decay value. And in this case, because this is reflection measurement only S111 parameter, we cannot measure the magnetic material. And also I make sure there's no air gap, because the air gap provide the bubble and affect the reflection. Of course, before the calibration, you have to do calibration. We have a variety of calibration methods available on our software. If you have your own standard definition, you can also do that yourself. Otherwise, typically people use air as open. Short, we have the short standard come with the probe, and distilled water, because water have its known dielectric properties. We have 3 different probes, 20 gigahertz, 50 gigahertz, and 50 gigahertz. So this one here is come in 3. This is more suitable for consumable, low-cost version. In this case, people use if people know that it's going to destroy the probe and use this one. This is more high-end probe that we have hermetically sealed on both ends, so that way you can test food or some other medical or even some chemical testing. Of course, we provide you with a raw material of the made of probe, so you have to make sure your chemical is not damage the probe. So this is an example of measure different type of sugar. This is a study done at one university that this is showing that 90% water, 10% different type of sugar. Looking at the decay or the real part of permittivity, you cannot easily identify, but you look at the imaginary part or or you can see the DF value, you can see clearly change on the top here. So what they do is they measure different type of sugar, and then they try to identify. So clearly you can tell that you can tell different type of sugar based on the grouping. This measurement is really, really sensitive. So meaning that you can actually measure a slight change. In this case, it's 99% water and 1% different type of sugar solution. You can still be able to tell that even with 1%, we be able to detect the difference between between the different type of materials. Some of the I think university in Malaysia actually used this probe to do some study because some of the culture they don't eat meat products, so they use this probe to try to detect meat product in food. For example, testing food to look for the chicken, beef, or pork. So each of these different meat have different dielectric properties can easily identify. So that's one of the studies that they did. So in terms of what's the benefit of this solution, the open coaxial probe is useful, especially if people do early or initial study, so that way you can use these, continue on with more vigorous method. It is simple and it can be correlated with some other property as well. And in terms of customer user base, I can say that about half of our customers start with this solution first, if the frequency is fit within 50 gigahertz or lower. So next will be the transmission line method. The transmission line method, this method able to measure both magnetic material as well as non-magnetic material. It requires network analyzer because we are using S parameter to calculate the DF or the decay value or the mu. It requires two-port calibration, meaning that if you're not familiar with the network analyzer calibration, especially with high frequency, you need to taking care of cable, calculus, things like that. And I believe I just published two YouTube Keysight University class talking about how to making the measurement at high frequency using different type of measurement methods. And you feel free to go to Keysight University web link, and then you can actually watch it for free. So in this particular case, the sample, if you are using waveguide, then your sample needs to be rectangular, fit inside the waveguide, and it gives you dimension here, depends on the sample thickness and the frequency. And for the airline, if you're not familiar with airline, basically it's coaxial with a pin. And in this case, your sample needs to be donut shaped. So the dimension I give you here, so that the sample needs to be fit inside as well as the hole, so that the center conductor can slide into. The advantage of using the airline is because more broadband. So in this case, from maybe let's say 500 megahertz to 18 gigahertz, because this is the type N. The waveguide is banded by the waveguide band. For example, X band would be 8.2 to 12.4 gigahertz only. So how it works, as mentioned, you require all 4 S parameters, and Keysight software option 001 transmission line method, and some of the measurement sample restriction, no air gap. Our software actually, without going to details, if you have air gap, your sample is not tightly fit, we have some way to correct the air gap as well. So if you need to know more detail, we can discuss. In terms of really high frequency, we do have different types of fixture. So this fixture is 60 to 90 gigahertz. We switch to 12, we call it. And the sample, basically, we just slide this open up and close the gap. The sample will go here. The reason for this is because at mmWave frequency above 50 gigahertz, the sample is too thin to fabricate to fit inside something like this. So we need to use this type of fixtures. And this is high frequency, 330 to 500. Of course, this is 1 to 500 to 750 gigahertz. So the transmission line method, we have different measurement models. I think you're familiar with all these models. So the Nicholson-Ross model can measure both magnetic and non-magnetic material, the epsilon and the mu, and the NIST model, precision model, the transfast model. This is Keysight proprietary model, so we don't actually publish the mass. But these are the two models here. This is public domain. And then, as I mentioned, if your sample is too thin, then we can actually have a support sample on both sides, so that knowing these two samples, we can actually de-embed these two samples. What's left is your actual material itself. Today's option, meaning available from Keysight, the transformation line method, we actually provide the measurement uncertainty of the Nicholson-Ross model. So because we are able to measure as parameter uncertainty, then we can use that uncertainty to calculate actual DF and DK measurement uncertainty. So that is available as of 4 months ago. It's new to Keysight. So in terms of summary of the transformation line method, so provide both epsilon and the mu, and fixture, simple fixture, well, I guess depends on your definition, and provide broad frequency, actually up to 1.1 terahertz. And then in terms of limitation, because the waveguide is really large and low frequency, then sample is really large, so it may not be practical. And limit to somewhat low loss measurement resolution. So I talk more about that in next few slides. And it's if you have liquid and it's kind of hard because get liquid to fit inside some waveguide is difficult. So next one is the transformation line, meaning a part of transformation line is called free space. So free space, the measurement method basically requires 2 antenna horns, and the sample will be inside. And it's especially useful for a high temperature measurement. So basically you would have the furnace here, and then you can heat your sample up to, we have solution with our solution partner up to 1,800 degrees C and up to 40 gigahertz. And we also have additional furnace and hardware that can operate up to 110 gigahertz. In this case, this method, your sample will not be disturbed, or because other methods you have to fabricate your sample to fit inside certain fixtures. In this case, you just put your sample inside the furnace and you can measure without disturbing your sample. So this is the fixture that used for free space. Obviously, at low frequency, the fixture or the antenna will be larger, and lower frequency it will be smaller. There is a solution that only requires single antenna. You can see here on the middle that can operate 18 gigahertz to 110 gigahertz. Again, I have the video that Keysight University class that actually show the steps of how to make the measurement. So you might want to look at that if you're interested into this free space measurement method. So it does require calibration. So the TRL calibration is the best. The through, which is nothing there, reflect. Yeah, if you put the metal plate in the middle, and then you have to move the antenna back to be the same thickness as your metal plate. And then the line, then you have to move additional space distance to accommodate for the quarter wavelength as well as your plate. So the fixture itself has the micrometer here to help guide how much you need to move in terms of the calibration. And this technique, if you don't have the micrometer, it might be difficult. However, but we do have the other we call the TRL calibration, which does not require this complicated step. Again, we can talk more in details if you want later. In terms of the measurement accuracy, this is measured the PTFE using 110 gigahertz system. your sample will basically go here, and the calibration I already talked about. You can see the measurement is really tight, PTFE, really tight, accuracy flat, and the loss tangent or the DF value and so low. In terms, if you want to go higher frequency, let's say 1 to 1.1 terahertz. So in that particular case, we have the network analyzer with the Virginia diode mmWave module with all the bands. You probably heard about now 6G research. Even though they don't have the specified frequency, but most of the work from my personal experience is around 300 gigahertz, so even 220 to 330. So this head had to be at that particular frequency. And you can see here in this table, this big piece metal at different holes. So this is help determine which frequency range that you want to use based on your frequency of interest. This is called a quasi-optical table. And the sample will go here to make the measurement. I have a little bit more in detail here. And this particular setup is up to 110 gigahertz. So the signal will go through here, and your sample will be here. This method actually is really good because precise the position of the fixture and no actual movement. So it requires calibration, of course, and the sample just go here, and we do a two-port calibration with network analyzer, no additional movement, higher frequency, less movement is better, so that way your S parameter is accurate. So to get accurate DF, DK value, you need accurate S parameter. So calibration, I just mentioned about using the GIL calibration. So in that case, it's much easier. Okay. So in terms of actual measurement result, I show here 750 gigahertz to 1.1 terahertz, measure PTFE decay, so roughly about 2. So which is super accurate. Okay. And this is, I believe this is the loss tangent value, okay, for PTFE. So to summarize about this free space. So free space is useful method to measure electromagnetic materials, and this is the calibration that overcomes some of the challenge in terms of moving precisely using the TRL calibration. And this is a Keysight offer best measurement solution at higher frequency. So down to one last method, so the cavity method. The cavity method, basically how it works is basically we measure the cavity or the fixture, because the fixture has certain dimensions based on the actual mechanical. It will resonate at a particular frequency based on the actual physical of the fixture, and then we measure empty fixture and the bandwidth or the Q, and then from that we insert the sample into it, and then because the sample change the effect of the Q, the bandwidth and the resonant frequency, and the difference, then we use this formula to calculate the DK and the F value. The fixture, if you have really high Q, then that gives you additional accurate in terms of the measurement resolution as well as the DK and DF value. So the key is to have a good fixture so that you can have accurate measurement. We have 3 different types of fixtures. So we call this is a split cylinder resonator, SCR. So this particular fixture is up to 80 gigahertz. We have 10 to 80 gigahertz. Again, this is a fixed frequency. We have another type, we call this is balanced type circular disc resonator. So in this particular fixture, provide you with different, with multiple frequency points, but it requires calibration. And we also have these peripheral resonator and can go up to 140 gigahertz today using different modes. If you want to know more details, you can get into it, but for now, let's give you high level. We have the low frequency one, we have the SPDR, split pulse dielectric resonator, up to 15 gigahertz, and using different software options, and this is the SCR split cylinder resonator, 10 to 80 gigahertz discrete frequency, this is connector here. Most today is for 5G FR2 around 28 gigahertz and 40 gigahertz. This is the balance resonator. We have two different frequency models, up to 67 gigahertz and 110 gigahertz. And we have another fixture from Keysight, original fixture that can actually operate up to 30 gigahertz. So depends on your frequency interest. For this particular one, if you want to have multiple frequency, that means you have to get different multiple fixtures. For this particular one, we specify at 10 gigahertz, but you can actually tune to around few other frequency like 13, 17, 22, and 29 gigahertz. So how it works? First, let's look at SPDR first. Basically, the simple. So inside there is a two cable or loop that do signal coupling, and your sample you slide in. The idea is you want your sample to be flat up against the bottom half. If your sample is away from the bottom, let's say towards the center, it actually affects your measurement accuracy. So if you want your sample to be flat, lay against here. So this could be the challenge if your sample is really thin, let's say 30 microns or 45 microns, for example. So your sample may be warped, towards the bottom. So that way it will affect your measurement. So you need to make sure the sample is thick enough. Okay. And this is the result. In this case, PTFE. So simple measure, empty measure with the sample, and the software will display the result for you. So the SCR high frequency. So in this case, I'm showing you with the USB VNA. Of course, USB VNA, you need to require a PC to run the software. So the measurement is simple: close, open, put the sample in. So that way you can measure easy. The measurement accuracy and repeatability, you can see the standard deviation, the average. You can see all these numbers at different frequencies, all really tightly repeatable numbers. So the BCDR. So this picture you can see here, and this is actually up to 67 gigahertz. So connect the cable to the analyzer and connect here. So basically, this method it requires a two-port calibration because the measurement is broad. So we want to make sure we can tell the signal at the resonant versus the noise floor. So how it works? Basically, here, so this is the electrode, the red portion, and the yellowish portion, your sample. In this method, require two samples. Your sample has to be identical and has to be precisely the same thickness. And the center red piece is called electrode. So it depends on the decay value, sample thickness, and this electrode disk. It will resonate at a particular frequency. You can control this resonant frequency by adjusting your sample thickness. When resonant at a particular frequency, what we're doing, then we take that frequency and we take its harmonic of that. So for example, if resonant at, let's say, 17 gigahertz, the next frequency point would be 34 gigahertz, and so on and so forth. And then for the 110 gigahertz, of course, using the millimeter wave, it comes with a little jack here. So that way you can jack up your sample, so that way you don't bend the cable, and you need to keep the cable really short because high frequency, your RF loss to the cable is significant. And then the bottom module is showing here. Okay, and of course the software run on the external PC or inside the node analyzer. So some of the example using the COP 180 microns. You can see here the first resonant frequency is 20 gigahertz. This is the real part of your permittivity or your decay value. And next will be the 40, 60, 80, 100, 120 gigahertz. And this is your loss tangent, your tan delta. This is picture show the actual measurement setup. You know, the heads down here, the other ones up here, moving up and down. And of course, before to do that, we had to do two-port calibration at the end of the cable here and here first before we connect to these fixtures. So the summary of this fixture, basically the cavity fixture is the best for low loss material. Actually, this is the only solution that's available for you if you want to measure really, really low DF value. The con or the limitation for this is because it limited frequency point. So in terms of overall resonant cavity versus broadband, because most of the time people want to measure, you know, multiple frequency points, they don't want to buy mini fixtures. So in comparison, so low loss for the resonant cavity, we can measure down to 10 to minus 4 in terms of measurement resolution for the DF or the imaginary part. Okay, but of course, different thickness and the fixture, you require different fixture. For the broadband, the measurement resolution is less, but you can measure multiple frequency point because just swap frequency. Okay. So since there are so many, basically I cover 4 or 5 major measurement methods available for Keysight. Of course, there are other methods that are available in the industry. So which method I should use? So the answer is not as simple as you may think. It all depends on the frequency of interest, expected value of your DF, which is the critical parameter. I'll show you why next. And the required measurement accuracy and measurement resolution, material property. Is it homogeneous, isotropic, or not? And then the form of your material, liquid, powder, sheet, and sample restriction. Because the material is only the material when signal propagates to your material, there is the X and Y plane propagation. So certain only limited measurement methods that actually can measure both X and Y can give you the same answer. So I'll tell you that later. So before you choose, so I refer back to this table or slide that give you an idea of how you can, make your decision. So the answer is which method to use. It all depends on the critical parameter is your DF or your tan delta value or your imaginary part. So if you expect the DF or your quality factor tan delta value is less than 0.01, use the resonant cavity method. This is the only method that's available for low loss material, and that is give you enough measurement resolution to get this type of accuracy. If it is greater than 0.01, then you can use the transmission line method or coaxial method. So this method will not give you the measurement resolution accurate enough if you have really low loss materials. With that, I think I hope I stay within time. Yes. So with that, I hope Davino can answer some of the chat questions, and if not, then I can entertain or answer any question that you have.
Sure. Thanks, Sai, for the presentation. I was just going to keep the questions till the end so everybody gets to hear it. One question on the presentation slides. We will be sharing them shortly along with the recording as well. So starting with technical questions, Sai, you presented a plot, I think in the slide 3 or 4, where you had a graph about the air, the lower dielectrics. So question here is, where do plastics fit in this plot? I believe it's usually under the lower dielectric values, but if you want to bring that up real quick, maybe.
I'm there.
Maybe the next slide. Oh, this one.
This
oh,
one.
yeah.
Yeah.
Oh, so I wanted to know.
I think, yes, I think plastic is, even remember correctly, around maybe 5 to 7, I believe. I don't remember exactly. Let's say polymer materials. I think between 5 to 7. So let's say 6 in average. Then that means that the propagation delay would be 8 nanoseconds per meter.
Got it.
So that means that you have to perhaps mix, if you want lower the decay, or if you want lower DF, then you have to perhaps mix with some other material that you can reduce your decay. The way you reduce your latency or your electrical delay, propagation delay.
Got it. Right. The next question is on the parallel plate method, the 16451B. They want to know what is the lower thickness that can be tested using the parallel plate method.
So, which
the 16451B.
16451B.
Yeah, the parallel plate. Yeah. What's the kind of a minimum thickness?
So we don't say minimum. What is minimum thickness? So what we usually say is, we don't give you the minimum thickness. I think we can say that usually around maybe 100 microns, maybe, because we measure the capacitance is too thin, and then the gap is maybe overwhelmed. The ratio of the air gap is too much. It may affect your measurement. I think we should say maybe around 100 microns.
Okay.
Minimum thickness.
Okay. So the next question is on the transmission line and waveguide. So what is the sample tolerance for waveguide and coaxial measurements, meaning the air gap tolerance that they're looking for?
Yeah. So we don't really have a limit on the air gap tolerance, but as long as we know precisely what the thickness of your sample, then let's say X band, WR90, I believe, X band. So the precisely dimension of our waveguide aperture already, and if you can measure precisely of your sample thickness and the the height and the width, and then the software has a correction value you can put in. So I think it's not a matter of tolerance, but it's a matter of knowing precisely. But the thickness itself is a critical parameter because we use that number to calculate the permittivity values.
Right.
So I would say, yeah. Yes, the thickness part is more important.
Got it. I think this is also respect to the transmission line and coax method. A question goes, can we measure dielectric constant and loss tangent of a material, which is a nanometer thin layer, often resting on a surface of a copper of 20 microns?
So the answer is because the measurement method, meaning the measurement model So the measurement model require a certain thickness, either quarter wavelength, half wavelength. So the minimum is 20 degrees. So 20 degrees divided by 360 degrees, I guess 1/18 of the wavelength. So you need to have your sample at least minimum 1/18 of the wavelength. So for X band, you need to pick let's say the middle of the frequency, let's say 9 gigahertz. Using that frequency, calculate your wavelength. So your sample needs to be at minimum at 1/18 of the wavelength. So it's kind of limitation indirectly limits the measurement of the transmission line limitations. And unfortunately, we cannot measure a layer. So all material had to be, so because the measurement is using S parameter, so only give you one S parameter phi, so we can only calculate a composite of all the whole material together. We cannot separate out in layers. So if you want to measure that thin, I would say, I would suggest 2 ways. One is measure your material without your, because you need to deposit your material into another material because it's too thin. You measure your transmission line without your material first and get S parameter for that. And then you measure another one with your base material and your material deposited on it and measure S parameter and then do external S parameter subtraction and then import that S parameter back into the software, even though you may violate the sample thickness 1/18 of the wavelength, it may give you answer. But otherwise, I would say using the cavity method maybe it's better. That way, it's more simpler because you can measure the cavity, empty cavity with your base material first, and then using that as your empty data, and then put in your material with the deposit, the sample, and then remeasure, and then we can calculate the dielectric property. But with that method, you cannot measure magnetic material. I hope that helps. The thin sample is really difficult to measure.
Mm-hmm. So the next question, I believe it could be either for the transmission line or the 16451B. They just wanted to know, when measuring powders, do we need to pack it? And as far as I can remember, there is a Petri dish that you need to use with the 16451B. Similarly,
yeah,
with the transmission line, I believe. So go ahead,
yeah.
Ty.
Yeah. So I think powder I would recommend using the transmission line because I think you can pack it inside, let's say you have let's say using the PCFE as your support, for example, then you can pack it so that, but make sure you know the thickness in this area here. So I think using the transmission line is better. There is people want to measure liquid. They create their own fixture. So it's like a tub, a capture. So what I suggest them to do is connect your fixture as your system, and that way your fixture is part of your calibration, and then you can put your sample in afterwards. That way your sample holder thickness is 0 and distance to sample is 0, and then you just put in your sample thickness, and that way you can calculate that way. But it's a sample powder and liquid. It's hard to measure because we need to have some type of containment.
Okay. So there are just a couple more questions. Probably we may need to top them off. One with regards to, are there references available for the analytical methods and how they're specifically implemented in the software? I believe we have some transmission line method papers on it. Go ahead, Ty, if you want.
I'm not sure if I understand the question, but if you're looking for a reference paper regard to our management methods or models, like I said, on our website, our support website, we have a management model that we actually tell you what paper that we use, to implement the management model. You can read those papers. I think most papers are IEEE paper you can actually buy from them. I'm not sure if I answer correctly.
Sure.
One thing I want to mention is if your company, I'm not sure if you heard of, it's called the INEMI project. I think it's called International Electronic Manufacturing Initiative. They actually have the committee of many companies do material studies that try to come up with the reference material so that the industry can use. So Keysight is member of that committee. So I think the project is supposed to be finished sometime the end of 2021. So they're going to publish paper of the study and give a reference material as well as measurement reference, so that the industry can use that material as a check standard, so that to verify your measurement setup.
Okay. Got it. I think there are just a couple of more questions, but we may be running out of time here. We definitely will be able to answer these questions offline. Leslie or Mike, do you have any last things to add?
I think there is one last thing that I need to share with Mike's comment. Let me go to the last slide. Oops, go too far. All the way down. I'm not sure what happened. There is a survey slide that I might need to ask people.
Yeah, that's okay, Si. Don't worry about it. Well, I'll just speak to that. So thank you, Si, for the great presentation, and Darwino for your assistance with the chat questions. I hope the material presented was valuable for all of you who joined us today. Really complex application, as you know, and it's quite possible you may have a use model or a question which was not addressed. We'll gladly follow up with you to discuss your unique needs, so please take 1 minute to complete the evaluation, include any follow-on questions, and we'll respond to everyone. If you have a current project which you'd like to do a deeper dive on, we're always available to help you, so please note this in your evaluation and we will follow up with you promptly. Thank you very much for attending today, and we look forward to working with you on your next material measurement project. Have a great day, everyone. Take care and be well.
Thank you.
Thank you. Thank you for your time.